Hey guys, welcome back. I'm going to continue on with the free response question that we started last week Friday. So let's pick this up where we were. We had done A 1 and 2, and we had finished B1. So let me pick it up at B2, and let's keep going. So let's make sure we got the lay of the land, make sure we understand where we are and what we're talking about again. We have a chemical reaction here. HCl can react with methanol vapor, which is CH3OH, to produce CH3Cl, as represented by the following equation. So we have a reversible reaction that we're looking at, and we're going to answer some questions about the reversible reaction. They give us a value of K, Kp, meaning we're using pressures. These are all gases, so we can use partial pressure for the equilibrium constant. And let's go to 2b, so or B2 rather, I apologize. So B, CH3OH and HCl are combined in a 10-liter sealed reaction vessel and allowed to reach equilibrium at 400 Kelvin. The initial partial pressure of the methanol is 0.25, and that of HCl is 0.6. Okay, so let's go to B2. Considering the value of Kp, the equilibrium constant, calculate the final partial pressure of HCl after the system inside the vessel reaches equilibrium. So we're going to solve for the equilibrium partial pressure of one of our gases. That sounds like an ice table if I've ever heard of an ice table. Let's set this up. All right. So I have my chemical reaction, which is H2SO4. That's not the right one, is it? That's definitely not the right one. Hold on. Bad teacher. Let's go back to where we were. CH3OH plus HCl is producing CH3Cl and H2O. It's got to be H2O. Yeah, that makes sense. Okay, sweet. So we want to solve an ice table for this. We want to solve for the equilibrium partial pressure of HCl. All right, let's set up what we know. I, C, E. Initially, the molarity of the methanol is, this isn't very efficient, hold on. Keep running back and forth. The molarity of the partial pressure of the methanol is 0.25. The partial pressure of the HCl is 0.6. And we have none of the products. Okay? Now, since we have no product, this isn't a Q versus K question. We must have to go to the right. And at equilibrium, we're going to get 0.25 minus x, 0.6 minus x, and we're going to get x and x. Now, we can set this up, and we can set up K. Kp equals products over reactants. So I have the partial pressure of CH3Cl multiplied by the partial pressure of H2O divided by partial pressure of CH3OH multiplied by the partial pressure of HCl. That's my setup. Now the algebra here is going to get a little ugly, but we can take advantage of something. We can take advantage of the value of K. Let's go back to the problem and look at K. K is 4.7 times 10 to the 3. That's a big number. Okay, that's 4,700. That's way bigger than 1, right? So if I think about that and I consider that big value of K, we don't actually have to finish the whole ice table algebra thing here. We can actually kind of like cut a corner, which is always a good thing. Well, cutting a corner on the AP test is a good thing to save yourself some time. So Kp equals 4.7 times 10 to the 3. Now, that's bigger than 1, way bigger than 1. What the heck does that mean? That means that our products are favored, right? Substantially favored. Like, way favored. To the point where, in reality, this kind of turns into like a limiting reactant problem. Because K is so big, we know that almost all of our reactants are going to turn into products to a ratio of like 4,700 products to 1 reactant. That's what that big value of K is telling us, right? So that's such a big difference in ratio that we can assume that we're just going to go to completion. We're going to go until something runs out. So we did this ice table. We set all this up. We could totally set up the algebra too if we wanted to, right? I could totally set this up where I have 4.7 times 10 to the 3 equals x squared over 0.25 minus x multiplied by 0.6 minus x. And then we'd get this whole ugly, nasty, quadratic situation, right? Where we've got like an x squared term in the top, an x squared term in the bottom. And normally in class when we've done this, we've done an early square root and life is easy. But when our numbers aren't the same, like they aren't on the reactant side, we can't do that. It doesn't work. So we're going to take advantage of this. We're going to take advantage of the fact that K is huge. K is big, meaning products are favored. This turns into a limiting reactant problem. And what happens is X approximately will equal 0.25. Because once X equals 0.25, methanol is going to go all the way to 0 at equilibrium, right? We're going to run out of a reactant. That's what we're kind of looking for, right? So let's assume that we have a huge value of K, products are highly favored. We're going to basically turn all the reactant into as much product as we possibly can. So what happens is we're going to run out of the methanol. And if we run out of the methanol, X is approximately 0.25, which means the partial pressure of, I'm sorry, this is partial pressure, I apologize. This should be ATM. Okay? Which means is the partial pressure of HCl is going to equal roughly 0.6 minus 0.25, or in other words, I'll move my face, sorry, 0.35 ATM. Okay? That's a little funky. We've never done that in class. So again, AP can kind of give you some wrinkles. They can give you problems that feel very similar to what we've done with just a slight little tweak. What's important here is we understand that the value of K is big, meaning the products are really favored. And as a result, it turns into a limiting reactant problem. And we don't have to do the crazy algebra to get an answer of 0.35 atmospheres for this part. Now, I was warning you last week Friday about labeling everything, right? So let's do that. This is problem 2B2. Okay, that's important. We need to tell or say exactly what work corresponds to which chunk, right? All right, let's go to the next problem. We are on 2B3. All right, let's check out the problem. 2B3 says, the student claims that the final partial pressure of the methanol at equilibrium is very small, but not exactly 0. Do you agree or disagree with the student's claim? Justify your answer. Okay, so we just figured out in part B2 that our reactants are going to turn into products pretty much until completion, right? Until everything runs out. The limiting reactant was the methanol. So they're saying that at equilibrium, we don't have 0 methanol. In other words, we don't have 0 of this reactant, but we have very close to 0. I agree. I think that's absolutely true, right? We still have to have something there if it's equilibrium. This isn't like fully going through the products, right? It's going almost all the way to the product because our K value is so big, but it's not 100% products. It's not. Is it close to 100% products? Yes. Is it 99 point something percent products? Yes. But we still must have a tiny little smidgen of our reactant here because otherwise it wouldn't be equilibrium. If it's not equilibrium, right, then we would have 0 reactants, but it still is at equilibrium. We still have a value of K, so we must still have some of that reactant. Okay, so now we got to word this thing. So how do we word this? Let's answer the question first. The question was, do you agree with the student, agree or disagree with the student's claim? The student claim is that the partial pressure is not 0 but close. Okay, yeah, I agree. So I would say, I agree. So I agree. The partial pressure of the methanol would be close to zero, but not exactly zero. Now we need to justify it. And again, it asked for justification, right? So let's explain ourselves. Here's my explanation. The reaction is at equilibrium, meaning we must have some quantity on both sides. We have to. That's not equilibrium otherwise, right? If we have zero on one side, that's not equilibrium. That's like a reaction that just is fully going one way and not the other way. Equilibrium means both ways are happening at the same rate. So I would have quantities on both sides. All right, let's keep going. Oh, we made it to C. 2C. The table below shows some data for the compounds CH3Cl and CH3Br. C1. Identify all the types of intermolecular forces that exist among molecules in CH3Cl. Okay, so they want the intermolecular forces. We just need to identify them. That's not bad. That doesn't require a long-winded explanation. We can just kind of point them out. So, 2C1. We are looking at CH3Cl. What kind of intermolecular forces are in this molecule? Well, first things first, everything. Absolutely everything. Everything has London dispersion forces. We don't even have to think about that. It just is what it is. Doesn't matter what they give you. If they're asking you to identify intermolecular forces, it's got London dispersion. Everything does. Okay. Does it have others? Well, let's think about this. We would have a carbon in the middle, hydrogen, 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 and then chlorine. This chlorine over here is more electronegative than the hydrogens are. And as a result, we would totally have a polar molecule. There would be a partial negative over here and a partial positive over here. This is polar. So if it's polar, we're also going to have dipole-dipole forces. Okay, so London dispersion plus now there's a third type, right? The third type is hydrogen bonding. Hydrogen bonding only occurs if you have hydrogens covalently bonded to fluorine, oxygen, or nitrogen. Do we have fluorine, oxygen, or nitrogen in this molecule? No, we don't. So I think we're done. We have London dispersion and we have dipole-dipole. London dispersion because everything has it, and dipole-dipole because we have a polar molecule, right? We have a partial negative region, a partial positive region, which leads to those dipole attractions. All right, 2C2. Let's see what we got. In terms of intermolecular forces, explain why the boiling point of CH3Br is greater than that of CH3Cl. So here we go. We have our data table. You'll notice that the molar mass of CH3Br is way bigger than the mass of CH3Cl. And the boiling point further down is higher for the CH3Cl than it is for it's higher for the CH3Br than it is for the CH3Cl. So they're telling us what's in the table, right? They're saying, okay, hey, this one has a higher boiling point than that. Tell me why. So let's try to explain that. Now, in terms of explaining that, we have to think about what affects intermolecular forces, right? Whenever you get asked a boiling point, melting point question, and they want you to compare, it's not really a melting point or boiling point question per se. It has everything to do with the intermolecular forces. That's what we're interested in, right? So the question is why are the CH3Br intermolecular forces stronger than the CH3Cl intermolecular forces? That's what they're really trying to ask us. And what we can think about is the polarity of these molecules is going to be really similar. Okay? If I were to draw out, sorry, this is 2C, 2, kind of, okay. If I were to draw out the other molecule, right next to it, I have carbon in the middle, hydrogen, 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 and bromine. Okay, extremely similar, same exact structure. This would be your partial negative. This would be your partial positive. And the difference is the chlorine and the bromine. That's it. So why does this one have stronger intermolecular forces? Well, if you look at the molar mass, right, this one's just flat out bigger. It has more electrons. So the electron cloud of CH3Br is larger. Okay, and as a result, CH3Br is more polarizable. Okay? That term polarizability, what that's trying to say is that the electrons in that molecule are able to be manipulated or shifted or pushed to a greater extent. And as a result, you get bigger partial charges, right? So same exact structure, just switching out chlorine and bromine. Why does the bromine molecule have stronger forces? It has stronger forces because it has more electrons and it is more polarizable. It takes up a bigger space. Those electrons are able to be pushed and manipulated more. So as a result, you get bigger partial charges. So the electron cloud of CH3Br is larger, CH3Br is more polarizable. And I should probably complete my thought there, right? Which leads to stronger intermolecular forces of attraction. Okay? So just completing my thought, right? Because if I just say it's more polarizable, I probably should state why more polarizability equals stronger forces. All right, onward and upward. Where are we now? We're on D. Oh, we're on the last two questions. How fun. 2D. A 2 milliliter sealed glass vial containing 1 gram of CH3Cl is stored in a freezer at 233. Calculate the pressure in the vial at 298, assuming that all of the CH3Cl vaporizes. Okay, we have temperature, we have volume, we have mass. This is the ideal gas law. This is PV equals nRT. We are going to solve for the moles using our mass here of the CH3Cl. We'll use that as N, plug in T, plug in L, and solve for P. Let's set this up. So I am going to convert my 1 gram of CH3Cl first. All right, let me bust up my calculator and periodic table. Lost my periodic table. We have a new one. All right, so CH3Cl, carbon is 12.01 plus 3 hydrogens, which is 3 times 1.008, plus a chlorine, which is 35.45. So I get a molar mass of 50.484. And I get how many moles of my CH3Cl? I get 1.98 times 10 to the negative 2. Okay, and that's moles of CH3Cl. And now we're going to use the ideal gas law, PV equals nRT. The end goal is to solve for pressure. We don't know what that is. Volume needs to be in liters. They gave us 2 milliliters. Okay, 2 milliliters is this many liters. Okay, I converted that in my head. If you don't want to do that in your head, Please write it out. Okay, there it is. 2 divided by 1,000 equals 0.002. Excellent. This is going to equal my moles, which is 1.98 times 10 to the negative 2 multiplied by R. The value of R is in your formula packet. We are using liters, and we're going to solve in terms of atmospheres just to make life easy. And we're going to use 0.08206 liters times atmospheres divided by mole times Kelvin. Speaking of which, we also have 298 Kelvin as our temp. And now we need to solve for P. Let's do this. 1.98 times 10 to the negative 2 multiplied by 0.08206 multiplied by 298 and divided by 0.002. I'm getting a pressure of 242 atmospheres. All right. Last chunk. We are on the very last problem. By the way, this is a long one, right? There are long ones and there are short ones. This is a long one. So let's take a look at D2. Explain why it would be unsafe to remove the vial from the freezer and leave it on a lab bench at 298 Kelvin. Okay, so let's reread the whole thing. I had a 2 milliliter sealed glass vial containing 1 gram of this liquid stored in a freezer at 233 Kelvin. The boiling point of this stuff is 249. So if I take it out of that freezer, it's going to go from liquid to gas. And that's what we said in part 1, right? We're going to say it vaporizes. So if I turn this into gas, what was my pressure? 242 atmospheres inside of a sealed glass vial. That is a lot of pressure. Do you think it's a great idea to have that sitting out at room temp? Okay, explain why it would be unsafe to remove the vial. Well, pretty obviously, this sucker is going to explode, or most likely have a very high likelihood that it will explode, right? So let's answer that. Let's explain that. Okay. This is unsafe. This would be unsafe because the pressure in the vial would be very high and potentially cause the vial to explode. That's all we need to say. All right, that is it. What I'll do is I'll post the answer key, the official AP answer key to this with this video. All right, so we've gone through everything. Between last Friday and today, here is the entire answer of question 2. All right, we answered the first question here last week. It was asking if this was a redox reaction. We figured out all the oxidation numbers and they didn't change, so it's not redox. 2 was asking us to solve for the grams of sodium chloride if we had 3 grams of HCl using stoichiometry up here. That's not too bad. 2b1 was asking if there would be a pressure change as we approach equilibrium. Well, we had 2 moles of gas on this side, 2 moles of gas on that side. I think that was for the other reaction, wasn't it? I think it's for this reaction, I'm sorry. 2 moles of gas over here, 2 moles of gas over here. So it doesn't matter which way you're shifting, you got the same quantity on each side. So the pressure is never going to change, regardless of whether we're going left or right. In 2b2, the one we started with today, it kind of looked like it wanted to be an ice table problem, but then they wanted us to solve for the equilibrium partial pressure of HCl. And we could do the whole ice table thing and do all the algebra, but it was really ugly algebra. So then we kind of just figured out that K is really big. That means products are favored. So very strongly favored. So essentially this turned into a limiting reactant problem all of this would get used up, or almost all of this would get used up, which means that our partial pressure of the HCl should be really close to 0.35. 2B3, again, the partial pressure of the CH3OH would not be 0, it would be very close, but again, it's at equilibrium, so we must actually have something on both sides. 2C was related to intermolecular forces. CH3Cl has London dispersion and dipole-dipole. 2C2 was asking about the why CH3Br has a greater boiling point, or higher boiling point, higher boiling point or vaporization point. And the reason was it has stronger intermolecular forces. Well, why are the intermolecular forces stronger? Because there's more electrons and it's a bigger molecule and it's more polarizable as a result. And then last but not least, D. I'm sorry, I didn't even label this part. Bad teacher, see? This is the stuff. 2D1, sorry about that. We wanted to calculate the pressure inside that vial once we've raised its temperature to 298. So we needed to convert our grams to moles and then use the ideal gas law to solve for pressure. And then part 2D2, why is it unsafe? Huge pressure inside of a sealed container. That's sketchy, right? That's basically a little bomb. So we don't want that. All right, that's it. I will go over more free response stuff this Friday, but I hope this is helpful. Again, please, if you have any questions on this, let me know. Thanks, guys.